Hi, good afternoon. I hope I am audible. So let's start this session. Okay.
Yes, sir. Good evening, sir. I'm
Good
new to
evening.
this.
Okay.
Actually, due to my academics, I wasn't able to concentrate for a few assignments, and today I'm new to this session.
Sure,
I
sure.
have
Thanks a
seen the
lot.
recorded videos, and
Okay.
today I'm attending it.
Okay. I hope you are catching up with the recording video and I hope you are following up the assignments as well.
Yes, sir.
Yeah. Glad to know. Let me present my screen. Okay. So today we will be looking in the concepts of synchronous reluctance machine. Okay. So synchronous reluctance machine is a kind of a unique type of excitation in the machine. It basically works on the principle of reluctance, where let me just check. Yeah, so where it tries to align with minimum reluctance path always, right? So I have some, I think, FEA plots. If I am able to show, I think that would be really helpful. Mm, yeah, in the meanwhile, I'm opening a simulation file. So in the meanwhile, let me tell you a bit about our synchronous reluctance machine. So its rotor has neither excitation nor permanent magnet. Okay. So to run any machine, we need two types of MMF. One is field MMF, other is armature MMF, right?
Sir,
So here, yeah.
could you
Yes.
speak little loud?
Okay, okay. You are not able to hear. Just a second. By any chance now, is it better? Or can you please
Yes, sir.
increase the volume of your system if possible? Yeah.
My
Okay.
volume is at maximum, and now it is better.
Okay. Okay. Great. Thanks. So, mm, yeah. So what I was saying that synchronous lattice motor works on the principle of reluctance, and any machine to generate torque or produce torque, it must have two components of MMF. One is field MMF, other is armature MMF. Right. And torque production depends on field. Let us suppose it is armature and angle between them if it is 90. I'm talking this in terms of DC machine where such kind of alignments are maintained and their torque is proportional to FA sine alpha, where alpha is this 90 degrees. Okay. Now here in the synchronous reluctance machine, we do not have any field winding, right? So how field MMF will be established in the machine? Do you have any idea? Okay, so let me tell you. So here, field MMF is also being supplied from the stator side, right? So we have a stator winding. Okay, one component of a stator will go into the field component and other will go into the armature component. How will that happen? So let us see. This is the D axis. This is the q axis. They are both in quadrature, right? Now, with d axis, at some angle, we are providing armature, right? Now, here a component of armature mmf will contribute as, let us call this angle theta. At d axis mmf, it will be fa cos theta, and here it will be fa sin theta, right? Now, what will be the equation of torque here? So torque will be proportional to fa cos theta into fa sin theta, right? Now, if we break it out, fa square cos theta sin theta. Now, can we write in terms of sin 2 theta? Fa square by 2 into 2 cos theta sin theta. Now further we can write, simplify it, fa square by 2 sin 2 theta. I hope this expression may be familiar to you, right?
Yes, sir.
Yeah, so this sin 2 theta, it depends, and it has only one component, that is armature mmf, and this sin 2 theta is kind of, so with theta generally torque varies as this, right? This being 90 degree at maximum in DC machine, right? 180, 0, 0. Now here at 45 degree, the torque will be maximum, okay? And it will vary like this. Let me show you geometry of synchronous reluctance machine. So let me present my different screen so that it should be visible. Mm, So I hope you are able to see my second screen.
Yes, sir.
Yeah, thanks a lot. Yeah. So I hope you can see the synchronous reluctance motor geometry here. Here, this white portion is nothing but air. So we create such a shape in the rotor so that it creates saliency in the machine. And as we provide three-phase balanced supply on the stator side, it creates an RMF, just like an induction machine, three-phase induction machine, right? And the rotor, as RMF will rotate, the rotor will try to catch that field, and always it will tend to align so that there will be least reluctance between a stator and rotor. Okay, so let me open that file also to better visualize the software is a bit slow, so kindly bear with me.
Okay, sir, no problem.
Okay, so until the software response, we will solve a couple of numerical problems. Okay, yeah. So the first question is we have three phase, 415 volt, 50 hertz, four pole, a star connected synchronous reluctance motor with XT as 225 ohms per phase and XQ as 7 ohm per phase. Resistance we can neglect. Now, the motor rated torque is 12 Newton meter. We have to calculate the D-axis component of the stator current. Okay, so to calculate it, we must know the relationship between torque and current in the synchronous reluctance machine. Do you have any idea about that?
Sir, your voice is actually a bit low. I'm not able to hear properly.
Oh, still, sorry about that. How is it now? Is it better?
Could you make it little bit high?
Okay. Mm, I hope it is better now.
Yes, sir.
Okay, okay, okay. Okay, so I'll speak here. I hope it is good enough, right?
Yes, sir.
Yeah. Sorry about that. So, what I was saying that to calculate the d-axis current of a stator, we must know the relationship between torque and current, right? So, Do you have any idea about torque equation of the synchronous reluctance machine?
Torque is directly proportional to I square. Is that correct, sir?
Yeah, it is correct. It is correct. I square. But here we need it to be broken in terms of D and Q axis, as I showed, right? Uh, Let us suppose this is ID, this is IQ. So if you go through the lecture, you will see one equation. Torque is 3 by 2 P by 2
3 by 2, 3 by 2,
LD
LD
minus LQ ID IQ.
by Q. Okay, sir.
Okay, so how I am writing? So let me derive it from here. So it is like FA cos theta, FA sin theta, as I wrote, right? And FA cos theta we can write as FD because FA cos theta is along the D axis. So FA I can write as FD, and FA sin theta I can write as FQ, right? So FD and FQ is nothing but the directly proportional to current. So that is why ID and IQ is coming in the multiplication, right? So you can see the derivation, and this derivation will lead you to this expression of torque. And this is very famous equation. I hope in the meantime you will be able to automatically remember it because it is a very common equation of torque in permanent magnet machine wherever reluctance exists. So if in any machine there are field provided separately, let us suppose salient pole synchronous machine. What is the expression of torque there? 3 by 2 P by 2 psi f IQ, okay, plus LD minus LQ ID IQ. So this is the torque component because of the field winding present there, right? And field winding is generally aligned on the D axis. So torque is the multiplication in quadrature. So psi f into IQ will be one component, and ID IQ into LD minus LQ is the. So this is the reluctance component, and this is electromagnetic. Okay. So in conventional synchronous machine with salient pole and field winding, this will be the expression. If in the next week or next to next week, you will go through the permanent magnet machine. So their psi f could be replaced with psi pm. In permanent magnet machine, psi f will be field mmf will be provided by permanent magnet. That is why we write it as psi pm. Okay, I hope you are getting the idea behind it.
Yes, sir.
Great. So now I have written the expression of torque, and we are given with the required parameters, right? So what can we do? We can derive ID IQ, ID in terms of IQ, and we have another component which is voltage, right? So this is one equation. Let me write it with different color. This is one equation. Other equation will be in terms of voltage because we want to have two different equations because we have two unknowns. One is ID and one is IQ, right? And we have to find ID. And if you can find ID, you can also find IQ if you know that overall current, because total IS square will be, sorry, not under root. IS will be ID square plus IQ square. Okay. Now we want to calculate voltage in the machine. Okay. So from this phasor diagram itself, let me cut it. Okay, so we have to ignore the resistance, otherwise we would have included the resistance also here. Along the d-axis, there will be inductance of d-axis, right? So we can write it as LD. We have LDID as a flux, isn't it? On the d-axis, phi d, we have LDID. Now, because of this flux, there will be one voltage, and that will be VQ. Because of the d-axis flux, there will be voltage, and VQ will be nothing but j omega LD ID. Why j omega is coming? Because V is nothing but d phi by dt. And if you take Fourier transform, it will be j omega phi. Okay. So this will be VQ. Any doubt here in VQ? Okay. Now, because of Q axis, there will be again in Q axis, there will be some reluctance, right? And because of that reluctance, there will be inductance as well. So
Yes,
this
sir.
will this will be LQ. LQ IQ. So phi Q will be LQ IQ. And because of phi Q, there will be one voltage that will be VD. And if you are considering this as positive axis, this is origin, this is positive, so this will be negative T. So VD will be J omega LQ IQ. Okay. But since this LQ IQ is already in Y axis, so if you take you know differentiation of that, like let me correct it to LQ IQ, they are already in Y axis, so we can write it as JLQ IQ. Now, if you are trying to derive voltage from that, then you have to take J omega of that, J omega into J. Now J and J will be J square, and J square is nothing but minus 1. So VD we can further simplify as minus omega LQ IQ. Okay. Now we have one vector as VQ, we have one vector as VD, right? And magnitude is omega LQ IQ. See, the voltage is along the D axis, but LQ IQ inductance and current will be from the Q axis. Similarly, VQ is nothing but omega LD ID. So what will be the resultant voltage here in terms of magnitude, if you can tell me? Yeah, so it will be under root VD square plus VQ square, isn't it? And if I further simplify it, because we have all the values, so now I can write omega under root LD ID square plus LQ IQ square. Okay. So this is the voltage expression in terms of d-axis current and d-axis inductance. Any doubt here?
No, sir.
Okay. If no doubt, then let us find out our, so this will be our second equation. We have two equations. We are given with the voltage, right? We are given with the reactance along the d-axis and q-axis. We have just two unknown parameters. Those are d-axis current and q-axis current. Now, let us derive from here only. So this V will be phase voltage, right? So we will plug in those values here. Voltage value is given as 415 volt. So since it is a star connected, so phase value will be divided by root 3 is equal to omega. How much is the frequency given? 50 hertz. Okay. So how much will be omega? Omega is nothing but 2 pi ns by 60 into under root. LD is not given, but XD is given 25. So 25 XD will be nothing but omega LD. So we have to divide it by omega. First, let us calculate the value of omega. Omega will be 2 pi ns by 60. N is given. No, N is not given, but number of poles are given, frequency are given. So 2 pi by 60. N is 120 F by P. So 4 pi F by P. P is 4, F is 50. 4 into pi into 50 divided by 4. So it is 50 pi. 50 pi radian per second. Yes, omega we have calculated. Now LD and LQ. What about LD? LD is given as 25 ohm. 25 ohm is given omega LD. So LD will be 25 by 50. Sorry, 25 by 50 pi. So LD is nothing but 1 by 2 pi. What about LQ? LQ is also given, that is 7 ohm per phase. Now LQ will be 7 divided by 50 pi. So we will leave it as it is. Or if you want, you can calculate the values as well. Okay, so we have LD, we have LQ. Now we will plug in all those values. Here it is 50 pi. LD ID. So LD is nothing but 1 by 2 pi ID square plus LQ IQ. LQ is nothing but 7 by 50 pi square IQ square. So we have first equation. Can you simplify this equation further?
Yes, sir.
Yeah. So please proceed with the simplification and let me know the value what it will come. It will, in the meanwhile, I'll check on the software whether it has responded or not. Okay, so let me write this value of equation, what you might have calculated. It will come out to be 0.5822 ID square is equal to 0.00633 ID raised to power 4 plus 2.42337. So please match it when you will derive this equation or simplify it. Okay, so this will be first equation. Now, if we plug in the values in the second equation or here in the torque equation, right, what we can write as torque is equal to 3 by 2. Number of poles are 4, so 4 by 2. LD and LQ. So LD is 1 by 2 pi. And yeah, so one thing to be noted that LD will be always higher than LQ, right? Then only you can produce a positive torque. And LD has lower reluctance compared to, or D axis has lower reluctance compared to Q axis. Okay. Now LQ also we have calculated. How much is it? LQ 7 by 50. ID, IQ. And torque we know that rated torque is 12 Newton meters. Okay. So if you simplify it, you will get the value of ID IQ is equal to 69.8. Please match this value as well on your own. So this will be second equation. This is first equation. This is second equation. From here, you can calculate the value of ID, and that will be 9.79 amps. Okay. Try solving this equation on calculator or on your own as well. You will get the same value, right? And once you have computed the d-axis of a stator current, now you can calculate q-axis of a stator current as well by plugging in this ID here. So IQ will be 69.8 divided by how much we have calculated ID as 9.8, and you will get equivalent to 7.13 ampere IQ. Okay, so yeah, this is the solution of this problem. Any final doubt in this question? Yeah, so I hope you are able to get the problem. So any doubt in this problem, this part?
Sir, I have got an answer like uh, root over 0.0253 IT square plus
Uh-huh.
0.001936 IQ square. Is that correct?
Uh, the correct value of ID is 9.79 ampere, and correct value of IQ should be 7.13 ampere. Anyway, you recheck again your values. Okay.
Okay, sir. Can you
Okay.
please summarize that solution for the problem?
Definitely, definitely. So we were given with certain parameters XT, XQ, right? And we were asked to calculate D axis of a stator current as well as Q axis of a stator current. So we are given the value of torque. We know the torque equation of synchronous reluctance motor in terms of D axis inductance and Q axis inductance. So that has been described with the help of equation 1. Now, second thing, we derive the voltage equation. In voltage also, there will be D-axis inductance and a Q-axis inductance as well as currents will be mentioned. So here we derive the equation of voltage, and we were given with the value of voltage as well, right? Phase voltage will be 415 divided by root 3, and we equated and we got two equation and two unknowns. One with the respect of voltage, other with respect to torque. And we simplified both the equations, we manipulated the equation, we plugged values into each other, and we got the value of D axis current as well as Q axis of current. I hope that is clear.
Yes, sir. Thank you, sir.
Yeah, thank you. Now, let us, yeah, I hope that simulation must be ready. So let us open that simulation file. Uh, what else? I hope my screen should be visible.
Yes, sir.
Yeah. So now, what you are able to analyze from this flux contour or flux lines, right? We have like distributed winding pattern, and this is the pattern of winding here. And with the distribution, we are creating three-phase RMF, and how they are rotating. Let me show you. See, the RMF from the stator side is rotating. Here, this is the stator RMF, which is rotating, and it is linked to the rotor via the minimum reluctance path. So the yellow part is the core part, rotor core. That from here also you could see. So this blue portion is the rotor core. The white portion is nothing but air. So we have cut out the lamination in such a way that Q-axis inductance should be minimum and Q-axis reluctance path should be maximum. So that's how this phenomena works. So that's how coupling happens here. It is also a brushless machine, right? So I hope you are able to get the idea behind working of this machine. How much pole you can see here? Uh, to identify number of poles from this figure is how many flux loops are happening there. How many flux loops are completed by the stator?
Four
A
poles,
state
sir.
Four poles exactly. So there are four loops present in the machine. So it is four pole machine, right? Excellent. So that's what I wanted to show you. Right. Here we place windings like that. If you want to see the linear pattern, so this is how windings are made. This is for phase one. It will be wrapped around the uh, ratio of slot per pole. So here I hope 24 slots are there. So 24 slots and four poles are there. So ideally 24 by 4, six slots should be there in between each wires, right? And if it is less than six, then you can see here, right? It is going, it is coming out in 7 and going to 13, right? So six slots there are in between. That is nothing but number of slots divided by number of poles. Okay.
Yes, sir.
Okay. So let's get back to the numerical problem as well, because until we see the motor physically or we are able to visualize, it is very difficult to solve the problems, right? And here we have also phasor diagrams as what I just showed, that voltages, current, and flux. So that all is being supplied from the stator. Let us let us come back to the problem solving part. Okay, so the second problem is yeah, again. So three phase, 415 volt, a star connected SYRM, which stands for synchronous reluctance motor, has a bore diameter of 105 mm. I hope you understand what is bore diameter, right?
Sir, could you please explain that? What is meant by bore diameter?
Yeah, so bore diameter is nothing but a stator inner diameter, which is nothing but rotor diameter plus air gap, two times of air gap. So from the center of shaft to the point where the stator starts, a stator portion starts. So that is basically called uh, bore diameter. Let me show you from that figure. See here it is written a stator bore diameter as 87.7 mm, right? So what is stator bore diameter? From here, this shaft center to this this point, this point where the stator is starting, a stator teeth is starting, right? So that is a bore radius. If you double that, that will be the diameter, right? So from this point to this, from this point of a stator teeth center to the another point of a stator teeth to this point, right? So that will be entire bore diameter. I hope you got my point, right?
Yes, sir.
So a stator bore diameter is given to us, and what we have to calculate is pole pitch. We have calculated pole pitch in past for induction machine as well as other machines. Here also we have to calculate pole pitch. So what should be the pole pitch here? Yeah, and I forgot to mention number of poles is 4. So pole pitch is nothing but how much circumference of the stator bore or the stator or rotor diameter is being occupied by one pole. As you just saw that there were 4 poles in the machine. So how much is the length of one pole? So that length on the stator bore area, that will be known as pole pitch. Okay.
Okay, sir.
So pole pitch we can write as, first we have to write the circumference of the bore corresponding to the bore. So that will be 2 pi r or pi into bore diameter divided by total number of poles are 4. So that will be your pole pitch. Okay. So this much section will be occupied by your one pole. And let us calculate this value. Pi into d is 105 divided by 4. You will get the value approximately 82.5 mm. Okay.
Yes, sir. Got the answer, sir.
Sure. Now, if you have got this value, can you also calculate the peripheral velocity for this same parameters?
Sir, could you please say again?
Yeah. So can you calculate peripheral velocity? Let me write it here. Is my voice volume is okay or is it low again?
It is actually slightly low, sir.
Okay, okay. Let me see what I can do. Okay, I hope it should improve now.
Yes, sir.
Yeah. So here we have to calculate the peripheral velocity, right? So how much will be peripheral velocity for this machine? And what is the expression of peripheral velocity?
I don't have any idea about this, sir.
Okay. Anyway, so peripheral velocity is nothing but r into omega, like angular velocity. If you try to convert angular velocity to peripheral velocity, that will be r into omega. Okay. And omega is nothing but r into 2 pi n by 60. And n is nothing but synchronous speed. So, and both diameter we had calculated. Now, bore radius will be how much? 105 mm divided by 2 into 2 pi into how much is the RPM? 2 pi 60. NS will be 120 into F by P. So, since it is 105 is in mm, so we can write as 0.052 into 2 pi by 60. 120. Frequency is nothing but 50 hertz. Pole is nothing but 4. If you calculate it, you should get the value as 8.92 meter per second. Okay.
Sir, I'm not getting this answer, sir.
Okay, you are not getting, how much you are getting the answer?
I'm getting like 3.063.
3.063 meter per second. Okay, so there might be calculation error either at my end or your end. So please verify once more. And if you are getting 3.063 consistently, then be stick with that. Okay,
Okay, sir.
good. Now, the next problem is we have to calculate the current angle, okay, for maximum power factor. For maximum power factor, we have to calculate current angle when the ratio of LD to LQ is given only. That is nothing but 40. So first thing is what is the current angle, right? We saw this is the D axis, this is the Q axis. There will be current that will make certain angle from D axis. Okay, this is a stator current. This angle is known as current angle. Okay. Now there is one equation that is derived for maximum power factor in terms of LD and LQ. If you go through the lectures, that tan theta is equal to LQ by LD. Okay, or tan alpha rather, since I have used here alpha. So tan alpha is nothing but LQ by LD. I hope that is very straightforward, isn't it? And we are given this expression as LD by LQ as 14. So tan alpha is equal to 1 by 14. So, so for maximum power factor, this current angle should be tan inverse 1 by 14. Okay. So could you please calculate how much this value should be?
Yes, sir.
Yeah, please. Sorry. Yeah, you calculate that, but I think this condition is true for maximum torque. For maximum power factor, it will be under root of it. Okay, so also consider this under root. Okay, sorry about that.
Sir, why is it root over LQ by LD?
Yeah, so if you go through the lecture, there is derivation of this maximum power factor condition. And for maximum torque condition, alpha is tan inverse LQ by LD. Okay, and this is considered in account of consideration of at which angle if there is saturation, right? So at same instant, power factor will not be maximum along with the maximum torque. There will be different condition, and it depends on you what you want. You want maximum torque. Basically, we want everything to be optimal, right? But that is not possible practically. So if you want only power factor to be maximum, you have to go ahead with this angle. Okay. Why? Because see, we have calculated the voltage vector here, isn't it? And voltage vector came in the second quadrant, right? If you visualize, your voltage resultant vector will be here in second quadrant, isn't it?
Yes, sir.
Yeah. So similarly, let me bring that vector to here, GS. And power factor angle is what? It is nothing but the angle between current and voltage, right?
Yes, sir. Cos phi.
Exactly, cos phi. So this is the power factor angle. To have the maximum power factor, we have to rotate the is vector more towards the q axis, isn't it?
Yes, sir.
Yeah. So to consider in consideration of those factors, like how much should be the current vector there, and as is will move towards the q axis, this v vector will shift this toward d axis, because why? As iq will increase, vq vd is nothing but omega lq iq. So vq will increase, and if vq will increase, this vs will further shift on the left hand. So this angle will further increase. Okay. I know this might be a bit complicated, but if you sit with calm mind and if you try to visualize how these vectors are moving, right, then you will be able to understand. So there will be one particular angle corresponding to which power factor should be maximum. And that angle is derived approximately, that is not accurate, approximately LQ by LD, of under root of LQ by LD. Okay, and similarly for having maximum torque, right, we should have sine 2 theta, or the angle between d axis current and q axis current, as maximum as possible. Or other hand, you can also optimize d axis inductance and you can minimize the q axis inductance. So whichever way is suitable, wherever in the situation, you'll have to adapt accordingly, and then you can optimize. So this is very generic scenario where you can just write alpha is equal to tan inverse LQ by LD for maximum torque condition. However, this does not applies every time, because from situation to situation this will change. So this is just an analytical approximate equation. Okay,
Yes, sir.
great. So for maximum power factor, this alpha, how much it came out?
Sir, alpha is equal to 14.9599. Is that correct?
Exactly. Yeah, it is correct. 14.95 degree. And for maximum torque condition, how much will it be? Maximum for maximum torque condition, it will be tan inverse 1 by 14. And how much will it be?
Sir, it is 4.0851.
5 degrees. So you can see the difference between condition of maximum power factor and maximum torque. So there are almost 11 degree of variation. And this is just from the equation. In the real scenario, it can vary much more. So that uh, you should take care about, right?
Yes, sir.
Okay, so moving on to the next part. I think fourth problem, a three-phase VSI feed, 415 volt, 50 hertz, four pole, a star connected synchronous reluctance motor. XT is equal to again 45 ohms per phase. XQ is equal to 10 ohm per phase. Okay. Again, a stator resistance is neglected. Now this motor is driving a fan load. Whose torque is proportional to square of a speed. Okay, and torque is equal to 10 Newton meter at 1500 RPM. Now a motor is controlled with in constant torque region as well as in the field weakening region, right? So in constant torque region, what happens that this is the characteristics of torque, and after base speed, torque reduces. And this is about torque, right? What happens to power? Power increases and should it tries to maintain constant value. Okay, so that is the characteristics of constant flux region. This is constant flux region, and this is constant power region. Okay, so it is operating as such. Now we have
Sir,
to, yeah,
in that graph, flux is varying and torque is constant, right, sir?
yeah. So here, till base speed, what is happening? That flux is also constant and torque is also constant, right? But power is increasing because power is nothing but it is directly proportional to speed. But torque, if you recall from the DC machine, is what? K phi IA. So if flux is constant, torque should be constant. If assume that current is constant, and generally in VSI, current is maintained at its rated value from the starting. So that is why torque is constant till base speed. Till base speed, you got the idea? How is it varying?
Yes, sir.
After base speed, what will happen? That we have to reduce the flux. Why? Because why this power is becoming maximum at this point and becoming flat afterwards? Because this is the limit where voltage limit has been reached by the machine. Voltage is nothing but what? Omega into under root LDID square plus LQIQ square. Right? So omega value has reached the base speed point where voltage value has been hit. Right? The limit has been reached. Now afterwards, if we have to maintain the voltage and we also have to increase the speed, then we have to reduce flux or current. But if you reduce the current, your power will reduce. So rather, we tend to reduce the flux. And that is why it is known as constant power region or flux weakening region. Because we are reducing flux to maintain power. Because power is important over base speed, right? So that's what we try to do here. I hope you got the idea.
Yes, sir.
Great. So these are the parameters given. Now we have to calculate ID At which condition? At half the rated speed, at 1500 by 2 rpm, and one fourth of the rated torque, which is 10 Newton meter by 4. Okay. So we have to calculate this ID for maximum transient performance, right? So for maximum transient performance, like as we are changing the input, our output also should try to catch immediately. So for that, there is one relation that has been derived in the lectures, which is LDID should be equal to LQIQ. Okay. It is being assumed that for maximum transient or immediate transient, D axis flux linkage should be equal to Q axis flux linkage. Because, and what does it imply? Since LD is anyway higher than LQ, so ID should be less than IQ. Okay. Now, are we given the relationship between D and Q axis? Yeah, XD and XQ are given. So first thing is that we can calculate omega, which will be again 50 pi, because 50 hertz and 4 pole we have already calculated. So omega will be 50 pi radian per second. Now, what will be LD? LD will be XD by omega. XD is 45 divided by 50 pi. So we have to calculate LD here. Similarly, LQ will be x cube by omega. X cube is nothing but 10 divided by 50 pi. And this will be, we will calculate, right? So 9 by 10 pi, so 1 by 5 pi. Okay. So here also you can see that LD is significantly higher than the LQ, right? From the values given in the problem. So from this, for maximum transient condition, we can calculate the relationship between ID and IQ, right? So ID by IQ will be equal to LQ by LD. LQ is 1 by 5 pi, 1 by 5 pi. LD is 9 by 10 pi. Okay. So if you calculate 5 by 2, 2 by 9, it will be 2 by 9. So approximately 0.222. So ID and IQ relationship. So you can see ID is almost 22.2% of IQ. So one relationship we have got. Now we have to take help of other equation to calculate the current, right? So which other equation we can take help of with these much given data? Okay, so I hope you are able to figure out this alternative approach where the value of ID and IQ you can derive that is directly given as torque, right? So torque equation should be nothing but 3 by 2 P by 2 LD minus LQ ID AQ. Now I think you can calculate from here the product of ID IQ. Okay, so what should be the product of ID IQ? Torque value is 1/4 of the rated, which will be 2.5. LD and LQ we have already calculated, isn't it? 2.5 divided by 3 by 2, 4 by 2. LD is 9 by 10 pi minus 1 by 5 pi. Okay, so from here, whatever value, please calculate it for me. Okay. Okay, so I hope you are able to calculate it, right? And it should come out to be equal to 7.494. Okay, so now we have two equations, two unknown. We can easily calculate the value of ID as well as IQ. So ID will come out to be, let me write the answer for you, 1.29 amps, and IQ should be equal to 5.81 amps. Okay. Now the second last problem is here for you. Calculate the height of the stator core of SYRM if air gap flux through the stator core of the induction machine with a net iron length of 6.23 centimeter is 1.57 milliweber. Let me write it for you, okay? If the air gap flux of 6.231 centimeter is 1.57 milliweber, assume that the stator code is designed to operate at 1 Tesla. Okay, so please calculate it for me. Okay, so if you know the equation of induction machine stator core height, I think you can easily calculate it, and that value is given by dcs is equal to maximum flux divided by 2bcs into axial length. Okay, and the value of flux is given as 1.57 milliweber to bcs is nothing but 1 tesla into axial length is given here. Oh, sorry, not axial length. It is the iron length, right? This iron length, which will be 6.231 into 10 to the power minus 2. Okay. If you calculate, you should get as 1.26 centimeter. Okay. Any doubt here? If not, then let's move on to the last problem. We have to calculate the square L of a 10 kilowatt, 415 volt, three phase, two pole, 3000 RPM, a star connected SYRM, and n cos phi is given as should be minimum of at rated load should be higher than 95%, and output coefficient is also given. How much? It is 2000. Now, can you calculate the d square L product? D square L is nothing but kilowatt rating divided by efficiency power factor product into psi p, which is nothing but output coefficient, into ns, which is nothing but rps. Okay, kilowatt is 10. N cos phi minimum we have to consider 0.95, which means sigma pi is also given as how much? 200. And ns we can calculate how much is rpm? 3000. So rps will be 50. 3000 by 60 divided by 50. So d square L will be 1052 mm cube. So this much volume is required for 10 kilowatt of synchronous electric machine. So that's all about week 7 assignment problems. Okay, and I hope you are able to understand the concept and you will be able to apply all the concepts into the assignment problems. And yeah, if you have any doubt, please ask. That's all from my side. I'll be here. If you have any doubt, please go ahead and ask. Okay, thank you very much.
Sir,